Welcome to lecture series on advanced geotechnical engineering, and we are discussing module 4 and which is on the shear strength of soils. In the previous lecture we introduced ourselves to different types of triaxial test. They are namely consolidated undrained triaxial test, consolidated drained triaxial test, unconsolidated undrained triaxial test and unconfined compression test. And we have also discussed that there is several other possibilities also with the triaxial test, wherein we can also perform this extension test in order to measure the tensile strength extension characteristics of a soil or tensile strength of a soil. So we are discussing about the stress paths in triaxial, and thereafter we will introduce ourselves to octahedral plane and Mohr Coulomb condition, and thereafter we will discuss about how we can actually determine elastic modulus from the triaxial test. So before looking into the the discussion, let us take an example problem wherein the problem reads like this: a drain triaxial compression test is carried out on a sample of soil known to have the effective stress strength characteristics as effective stress parameters, and they are basically C dash is equal to 10 kilopascals and phi dash is equal to 22 degrees. If the cell pressure is 100 kilopascals, and draw the Mohr stress circle at failure and evaluate the failure values of T, S dash, Q and P dash, and draw the the stress paths on both T, S dash and Q, P dash diagrams. So, and what are the slopes of the stress paths? Evaluate K dash or A and alpha dash or psi. So we should actually refer here that there are two types of parameters, composite stress parameters. One is actually put forward by MIT group and Cambridge group, and both the groups actually have used, unfortunately, same symbols. They are Q and P. So for convenience here, Q is also defined as T and P is also defined as S. So as far as the composite stress parameters definition, such as the deviator stress and mean effective stress are basically widely used in soil mechanics, and in the course of the lectures also here and there we have used both MIT group and Cambridge group Q and P symbols, but here we are distinguishing with MIT group and Cambridge group the symbols put forward by MIT group and Cambridge group, where T is equal to T dash means that is nothing but sigma 1 minus sigma 3 by 2, which is equal to Q to the original definition put forward by MIT group. S is equal to sigma 1 plus sigma 3 by 2. So in case of S is equal to S dash is equal to sigma 1 plus sigma 3 by 2 is equal to sigma 1 plus sigma 1 dash plus sigma 3 dash by 2. But in case of Q, it is Q is equal to sigma 1 minus sigma 3 by 2 is equal to T. And whereas the Cambridge group, if you look into it, it is P is equal to 1 by third of sigma 1 plus 2 sigma 3 by 1 by third of sigma 1 plus 2 sigma 3, where P dash is equal to 1/3 of sigma 1 dash plus 2 sigma 3 dash. So Q is equal to Q dash is equal to sigma 1 minus sigma 3 according to Cambridge group definition of composite stress parameters. Now from the given data, the cell pressure was actually given as 100 kilopascals, and the soil actually was found to have has been given as the Mohr Coulomb failure envelope was given in the problem. So what we have done is that we have drawn the Mohr Coulomb failure envelope, and on the y axis, that is the tau, and the x axis it is sigma dash. So here this ordinate is 10 kilopascals, which is the the cohesion ordinate, and the 22 degrees is the friction angle. Now for the we know that the sigma 3 is 100 kilopascals, that is actually at this point it is given. Now what we do is that the radius of the stress circle at failure can be obtained like this. So radius is nothing but the radius of the circle is nothing but which is you know, if you take this triangle, which is nothing but 10 cot 22, 10 cot 22 plus 100 plus r sin 22. So if you take this one, the radius is actually obtained here, and once the radius is obtained with this as a center and with this as one of the points, the more circle actually is drawn, and sigma 1f can be obtained as 100 is the sigma 3, so 100 plus 2r, that is the radius 2 times radius, we get the sigma 1 dash f, that is the major principal stress at failure. And once we get the major principal stress at failure, this S dash f can be obtained as that is nothing but sigma 3 plus sigma 1 minus sigma 3 by 2, which is nothing but 100 plus r, which is about 174.7 kilopascals, and QF is nothing but 2r is equal to 149.4 kilopascals. QF is nothing but that is sigma 1 minus sigma 3 by 2 into 2. So because Q is equal to sigma 1 minus sigma 3, so R is equal to sigma 1 minus sigma 3 by 2. So what we have done is that QF is equal to 2R is equal to 149.4 kilopascals, and P dash F is equal to 1/3 of we know that this sigma 1 dash which is 174.7 plus 2 into 100. With this what we get is that is sigma 1 dash is nothing but 249.4. So sigma 1 dash is nothing but 249.4 plus 2 into 100, we will get the P dash. So so according to the problem, we have been asked to determine Q dash and P dash, that is according to the Cambridge group. We have determined like this: QF is equal to sigma 1 minus sigma 3, and P dash F is equal to 1/3 of sigma 1 dash F. Sigma 1 dash F is nothing but 100 plus 2R, so this is this point plus 2 into 100, we got this one. Okay. Now what we actually next we have said is that we can actually get the the stress paths. We have been asked to draw the stress path for TS and QP dash. So for both the things here we have been given that this is P dash and this is Q, and we know that the slope is actually will be 3:1, 3:1. So the Q is 149.8 kilopascals, that is 149.8 kilopascals, that is this one, 149.4, that is here, it is plotted here, and this is 100 up to that is the cell pressure which is applied. So it traverses from here to here to failure. Similarly, when we take T is equal to Q is equal to sigma 1 minus sigma 3 by 2, S is equal to P is equal to sigma 1 plus sigma 3 by 2. So this traverses like 100 plus this is nothing but sigma 1 plus sigma 3 by 2. So this can be obtained like this is nothing but 174.7 kilopascals, so that is indicated here. So the slope of this is 1. So the T failure is around 74.7 kilopascals, and this is nothing but 174.7 kilopascals. So it can be seen that T S dash stress path has a slope of 1:1, and QP dash stress path has a slope of 3:1. So TS with the MIT group definition, the stress path actually has a slope of 1:1. With Cambridge group definition of Q and P dash, it is 3:1. Now we have been asked to determine K dash and K dash and alpha dash. So we know that we have a relationship between Kf line and Mohr Coulomb failure envelope. When we have the Q and P and when we have the tau and sigma, when we compare from the geometry of the two circles, we can actually we have derived that sin pi dash is equal to tan psi is equal to tan alpha dash, and where C is equal to this ordinate C is equal to A by A or K dash by cos phi dash. So by comparison from here from the two circles, we can get K dash is equal to, from this equation, K dash is equal to 10, that is C is given as 10 kilopascals, 10 cos 22, that is around 9.3 kilopascals. So that means that we are actually getting that A or K dash as 9.3 kilopascals in Q and P Q and P space, and tan alpha dash is equal to tan psi is equal to sin phi. So sin phi dash is given as sin 22, phi dash is 22 degrees. So tan alpha dash is equal to sin 22 degrees, which is nothing but alpha dash is equal to 20.5 degrees. So this alpha dash is equal to psi is equal to the inclination of the KF line is 20.5 degrees. So like this, we need to look into the same for getting the different parameters at failure from the basic data, which is actually deduced from the the triaxial test. Now let us consider the consolidated drained tests and stress paths. And when we have the isotropic consolidation, the constant isotropic stress, that means that we have got equal stress in vertical and horizontal direction. Then in that case, the Mohr circle is nothing but a point where the sample of soil under isotropic stress basically has a Mohr circle of 0 radius. So it is nothing but when we have a sample of soil under the isotropic stress conditions, the Mohr stress circle has 0 radius, and which is nothing but a point. So A is nothing but the total stress point, and A dash is nothing but effective stress point. And here for the sample consolidated at constant confining stress, the stress path is a single point with U is equal to 0, and sigma F is equal to sigma R dash, sigma R is equal to sigma R dash at the end of consolidation. So this is the initial state of stress at the application of the stress sigma 3. Then the Mohr circle will be a point that we have discussed. Now when the stress traverses to along the line with the tau is equal to 0, so this increment in pressure is carried by the pore water itself. The increment in pressure is carried by the pore water itself. So it actually traverses along the sigma line or sigma dash line, and further once at the end of the consolidation, the pore water pressure dissipates. So if the increment of pressure is actually carried by the pore water pressure is here, and once at the end of the consolidation, that du delta U actually dissipates. So if the total stress increment delta sigma is now removed, the stress paths will be reversed in the opposite direction. So it has actually traversed like this, but if the total stress increment delta sigma is now removed, the stress paths will be reversed. So triaxial test is restricted as the cell pressure must be equal to the minor or major principal stress, and wide range of stress paths are possible because of axial and radial pressure can be varied independently, and axial and radial pressures may be increased or decreased or held constant. So with that, what we are actually deliberating is that number of types of tests which are possible and can lead to different stress paths. So the CD test with the drained triaxial stress paths, compression where constant isotropic total stress. So here delta sigma R is equal to 0, compression where constant axial stress is 0, that is delta sigma A is equal to 0, and then extension the constant isotropic total stress where delta sigma R is equal to 0, and extension where constant axial stress where delta sigma A is equal to 0. So possible combination of drain loading in triaxial sample are discussed here. Now let us consider the drained compression, the constant isotropic stress, that delta sigma R, that means that the change in radial stress is 0, delta sigma R is actually 0. So in a drained triaxial test, sigma A is equal to sigma dash A and sigma R is equal to sigma R dash. So and then U is equal to 0, this is because the pore water pressure dissipation is 0. So delta sigma A dash is equal to delta sigma A, delta sigma A dash is equal to delta sigma A dash, which is positive, and delta sigma R dash is equal to 0. So if you look into this, delta T is equal to delta tau is equal to delta tau is equal to delta sigma A minus delta sigma R, that is nothing but delta sigma 1 minus delta sigma 3 by 2. So if you look into this here, delta sigma R is equal to 0, with that what we have get is that delta sigma A dash by 2, and this is delta tau is equal to delta A dash by 2. And when you have delta S dash is equal to delta sigma dash, then delta sigma dash is equal to delta sigma A dash, that is nothing but a delta sigma 1 dash, plus delta sigma R dash, which is nothing but delta sigma 3 dash divided by 2. So with the delta sigma R dash is equal to 0, what we have got is that this delta sigma A dash by 2. So the slope of this one delta tau by delta sigma dash is nothing but the positive, that is nothing but if they get cancelled, then delta tau by delta sigma dash is equal to plus 1. So only the stress which changes is sigma A dash by an amount delta sigma A dash, that is nothing but the axial stress is actually increased, and the rest everything delta sigma R which is sigma R dash is equal to 0, and in the drained stress path compression constant isotropic stress where delta sigma R is equal to 0, and with that the pore water pressure dissipation both during the shearing is 0. So this is can be indicated whatever we have deliberated with drained compression with constant isotropic stress where delta sigma R is equal to 0, with compression on the upper axis and extension below. So and sigma and sigma dash axis here. So M is that point where initial stress point, and then what we have said is that the stress path actually traverses to M to P, MP, and the slope of this line is delta sigma by delta tau by delta sigma dash is equal to positive 1. So that is nothing but because of this deliberation what we have discussed here in this slide, the slope of this line is 1. The slope of this line is 1 vertical 1 horizontal, and this is the KF line, this is the KF line. So if you look into this, the stress path is a straight line with the slope 1:1, that is actually 45 degrees failing at point P. So the slope is actually meeting the KF line at point P. So MP is the stress path is a straight line with slope 1:1 failing at point P. Now drain compression constant axial stress, that means that here delta sigma A dash is equal to 0, that means that there is no change in the axial stress. So here what we have got is that the only stress which changes is delta sigma R dash by an amount delta sigma R dash, that means that we are actually increasing, let us say delta sigma R dash. So delta sigma A dash is equal to 0, and delta sigma R dash is equal to minus delta sigma dash. So delta tau is nothing but delta sigma A dash minus delta sigma R dash by 2, with that what we get is the delta sigma R dash by 2, and delta sigma dash is equal to delta sigma dash A plus minus of delta sigma R dash by 2. So with that what we get is that delta sigma A dash is equal to 0. So with that what we get is that minus delta sigma R dash by 2. So when we have let us say the sample delta sigma A dash is equal to 0, and when you keep on increasing delta sigma R dash, the sample experiences the delta tau by delta sigma dash is equal to the slope will be minus 1. So that means that 1 vertical minus 1 horizontal, you can see here. So in this case when you have the constant axial stress delta sigma A dash is equal to 0, that means that there is a constant axial stress, and if the stresses are initial isotropic, the resulting stress path is given as MR, that is that if the MR is the resulting stress path which is actually which has actually got a delta tau by delta sigma dash is equal to minus 1 with K naught is equal to 1. Now drained extension, the constant isotropic stress where delta sigma R dash is equal to 0, that means that here in the drained triaxial test sigma A is equal to sigma A dash and sigma R is equal to sigma R dash and U is equal to 0. So here the only stress which changes is sigma R dash by an amount delta sigma R dash. So the only stress which actually changes is delta sigma R dash by an amount delta sigma R dash. So in this case delta sigma R dash is equal to 0, that is and then delta sigma A dash is equal to minus delta sigma A dash, and delta tau is equal to minus delta sigma A dash minus delta sigma R dash by 2, and with delta sigma r dash is equal to 0, what we get is that delta tau is equal to minus delta sigma a by 2, and delta sigma dash is equal to with delta sigma r dash is equal to 0, what we get is that minus delta sigma a dash by 2. So delta tau by delta sigma dash is equal to plus 1. So if you look into this here, what we have got is that delta tau is equal to minus and delta sigma dash is equal to also minus. So the stress path is here, MQ is a simple extension of the corresponding compression test MP into the extension stress zone. So here the delta tau by delta sigma dash is equal to positive, but they have one with minus 1 vertical, minus 1 horizontal and towards the extension side. So MQ is the simple extension of the corresponding compression test MP into the extension stress zone. So for the drained extension, the the constant isotropic stress is delta sigma r dash is equal to 0 is actually given as the stress path MQ is a simple extension of the corresponding compression test MP into the extension stress zone. That means that we actually have discussed this one which is in the compression test, and this is actually resulting in the in the extension zone. Now we have another case that drained extension, the constant axial stress delta sigma a dash is equal to 0, and where delta sigma a dash is equal to 0, where delta sigma r dash is equal to plus delta sigma r dash. So delta tau is equal to delta sigma a dash minus delta sigma r by 2, where with delta sigma a dash is equal to 0, delta sigma a dash is equal to 0. So what we have is that minus delta sigma r by 2, and delta tau dash is equal to delta sigma a dash plus delta sigma r dash by 2, with delta sigma a dash is equal to 0, what we get is that delta sigma r dash by 2, with the slopes delta tau by delta sigma dash, which is nothing but minus 1, So the only stress which actually changes is sigma r dash by an amount delta sigma dash. With what here delta sigma a dash, that axial stress is actually not changed. So with that, what actually we get is that the stress path MS is a simple extension of the corresponding compression stress path MR, that is what we have indicated like this, into the extension stress zone. So this is nothing but the where delta tau by delta sigma dash is equal to delta tau by delta sigma dash is equal to minus 1. Delta tau by delta sigma dash is equal to minus 1 for a k naught is equal to 1 condition, but this is for isotropic case. So we actually have seen the various stress paths, but in this particular slide a simple isotropic compression stress path is actually shown. We said that it actually traverses along Ts dash, that is S dash line, and when you have got 1D consolidation, one dimensional consolidation, where there is only vertical strain and sigma epsilon r is equal to 0, axisymmetric case, where you have that k naught line is like this. This is the k naught line. So this is on this the 1D consolidation actually happens. But when you have let us say for a direct shear test, when the direct shear test when you draw initially this AB is actually very similar as the k naught line. So it traverses from A to B, because we in dry shear test what we do is that initially there is some vertical stress is actually applied, and before commencement and before shear there is elastic equilibrium or k naught condition is established. So AB is the along the k naught line. So there is a point B where when the shear started, what you can see is that BC is the path which actually takes the stress path which actually takes in direct shear test during shearing. So indicating that the tau added to the sample horizontally does not change yes, does not change basically yes, but just only T will change. That what you see is that the T is changing, but what is actually happening is that only the T changes, SC will not change. That means that the line traverses vertically upwards. This is in case of a direct shear test. So in reality basically S may increase slightly due to the passive pressures which are actually developed at the sample ends in the upper portion of the sample. So that means that indicating that the tau added to the sample horizontally does not change. So this figure, which is actually the stress path which is actually shown, indicates that the tau which is actually subjected to the sample, it does not change horizontally with S, but only the T is actually changing. So in reality S may be subjected to slight increase due to passive pressure developed by the sample ends in the upper part. So this is actually one of the limitations of the direct shear test. This we have discussed earlier. Now when you have got the triaxial compression and extension test, what we have discussed is that either with one vertical one horizontal 45 degrees case or in this side, this is in the towards the compression side, this is towards the extension. So this is shearing in compression and this is actually shearing in the extension. So shearing in extension means how it comes. So AB isotropic consolidation is here, and then when it actually BC, it actually changes from here. There is shearing in the stress path BC is the shearing in compression, and stress path BD is shearing in extension. So consolidated undrained triaxial stress. So till now we have actually discussed about the stress paths for the consolidated drain test. So the in case of consolidated undrained triaxial test, what we have discussed is that during consolidation the drainage is allowed, but during shear the drainage is not allowed, so that there is a possibility of the build up of the pore water pressure. And then we also discussed that depending upon the stress history and the type of the soil deposit, like a loose sand or a dense sand or normally consolidated clay or over consolidated clay. In case of loose sand and normally consolidated clay, there is a possibility that the pore water pressure, excess pore water pressure developed during shear is positive, and when you have a dense sand and or over consolidated clay, the pore water pressure developed is negative in nature, that is because of the phenomena of the dilation. So the isotropic consolidation, in increasing isotropic, the stress path for isotropic consolidation remains identically same in both CD and CU triaxial tests. For a isotropic compression case, initially both CD and CU, they are actually one and the same. So this we have discussed. So more circle actually initially a point with the 0 radius, and stress path traverses along the tau is equal to 0. This we have discussed during our discussion on the consolidated drain triaxial test. So this is at the end of dissipation of pore water pressure. It actually the stress of the sample increases by delta sigma dash, which is nothing but the amount of pore water pressure which is actually dissipated during consolidation. And here we have two cases: one compression, the constant isotropic total stress delta sigma r dash is equal to 0, and constant axial total stress where delta sigma a dash is equal to 0. So possible combinations of undrained loading on the triaxial test are shown here, where both are compression. One is that constant isotropic total stress delta sigma r dash is equal to 0, there is no change in the radial stress, and in the other case is that there is no change in the axial stress. So first case is that the constant isotropic stress or delta sigma r dash is equal to 0 when you consider. Then we have the slopes of the stress paths in conventional undrained compression are found to be by putting delta sigma r is equal to 0, and then with that we get delta tau is equal to delta sigma a dash by 2, and delta sigma is equal to delta sigma a by 2, and then the ratio of delta tau by delta sigma is equal to 1. So the effective stress paths will be separated by pore water pressure value u at any time. So before discussing the stress paths of in case of consolidated and drain triaxial tests, we should actually also introduce ourselves to two parameters which are actually put forward by Skempton. They are called as the Skempton's pore water pressure parameters. And a simple way to estimate the pore water pressure change in undrained loading in terms of total stress changes is actually given by Skempton 1954, and which is given by an equation delta u is equal to, this is delta u is equal to B into delta sigma 3 plus A into delta sigma 1 minus delta sigma 3. A and B, the both are called as Skempton's A parameter, A and B parameter. So B is a coefficient indicating the level of saturation. So if B is equal to 0 is basically a dry soil, and B is equal to 1 indicating that the soil is completely saturated, and A is nothing but the excess pore water pressure coefficient. A is nothing but the excess pore water pressure coefficient. So B is equal to 1 for saturated soils. When you put B is equal to 1, when B is equal to 1, and then delta U by then we can actually write A is equal to and AF is equal to delta U by delta sigma 1 minus delta sigma 3. So at failure with B is equal to 1, we can write A is equal to AF is equal to delta U by delta sigma 1 minus delta sigma 3. So what we have done is that further this particular equation we have taken, delta U is equal to B delta sigma 3 B into the brackets delta sigma 3 plus A into delta sigma 1 minus delta sigma 3. Let us divide this entire Skempton equation by delta sigma 3. So what we get is like this, delta U by delta sigma 3 is equal to B into 1 plus A by 1 plus A into delta sigma 1 by delta sigma 3 minus 1 delta sigma 1 by delta. So Skempton's equation is very useful in determining whether the soil is saturated in axisymmetric test. So during isotropic condition, delta sigma 1 is equal to delta sigma 3. So during isotropic condition, delta sigma 1 is equal to delta sigma 3. So when you substitute in this, what we get is that B is equal to delta U by delta sigma 3, when B is equal to delta U by delta sigma 3. So when during the isotropic consolidation, we maintain the delta sigma 1 is equal to delta sigma 3. So with that, when you substitute here, delta U by delta sigma 3 is equal to B, what we obtain. So for saturated soils, B is equal to 1 and B is equal to 0 for dry soils. So A parameter at failure, AF is nothing but, for normally consolidated clays, AR is equal to 1. So normally consolidated soils, the AR will be equal to 1, and for heavily over consolidated soils, AF will be negative. That area, the excess pore water pressure coefficient at failure will be negative. So the B parameter basically is a function of saturation, and A parameter is basically a function of over consolidation ratio. So over consolidation ratio, if it is high, then it actually changes into a negative. If for heavily over consolidated clays, that AF will be negative. So this particular table, which is actually gives typical AF values for a highly sensitive soils, the 0.7 to 1. And normally consolidated soils clays 0.5 to 1, and if you look into this compacted sandy clay, that AF value is 0.25 to 0.75, and lightly over consolidated clays actually have got 0 to 0.5, and compacted clay gravel has got minus 0.25 to plus 0.25. Heavily over consolidated clays can actually go up to minus 0.5 to 0. So if you look into this here, when the plot which is actually gives variation of AF with OCR, with increase in OCR, you can see that here it is 1, 2 and 3. So OCR actually more than 3, that is from OCR is equal to greater than 2 is set as lightly more than lightly over consolidated clays. So when you actually have got OCR in the value in the range of more than 3, the AF value will be negative. So this is actually the discussion we actually had earlier. If you connect, this is because of the negative pore water pressure development which actually takes place in case of during shear, in case of the over consolidated or densely deposited soils. So the undrained compression, constant isotropic stress. Now what we, with the background of the Skempton's pore water pressure parameters, we actually write the pore water pressure equation again with delta U is equal to B into delta sigma 3 plus A into delta sigma 1 minus delta sigma 3, and at failure A is equal to 0.33 to 1 for normally consolidated clay, and so for B is equal to 1 for saturated clay, when you substitute here, what you get is that delta U is equal to A delta sigma 1 plus delta sigma 3 we have taken common into minus 1 minus A. So here what we have got is that delta sigma 3 into 1 minus A. So here delta u is equal to A delta sigma 1 plus delta sigma 3 into 1 minus A. So delta sigma r is equal to 0 and delta tau is equal to delta sigma A by 2. So this is delta sigma r is equal to 0, there is no change in the radial stress, but delta tau is equal to delta sigma A by 2. So when you substitute this, delta sigma A is nothing but delta sigma A is equal to 2 into delta sigma A is equal to 2 into delta tau. So when you put here delta u is equal to A into delta sigma 1, A into delta sigma 1, with this, when there is no change, this becomes 0. So what we have is that delta u is equal to A into delta sigma 1. So delta sigma 1 is substituted by 2 into delta tau. So what you get is that delta u is equal to 2A delta tau, 2A delta tau. So A is equal to 0 to 0.25 for heavily war consolidated clays. Now further, this delta u is equal to A into delta sigma 1 is equal to 2A into delta tau, and where if A is constant during the test with the effective stress path, this is a straight line with the slope as delta tau by delta sigma is equal to 1 by 1 minus 2A, 1 by 1 minus 2A. So here if you look into it, here you have got delta u by delta sigma 1, which is nothing but 2A by delta sigma. So what we get is that if A is constant during the test, the effective stress path is a straight line with the slope is nothing but delta tau divided by delta sigma dash is equal to 1 by 1 minus 2A. So this is nothing but the slope of the the stress path, which is indicated in this diagram. And here in case of this is the total stress path, and this is the effective stress path, you can see that, and this difference is actually because of the delta u during the shear. So the slope of this line, if A is constant, the slope is nothing but 1 by 1 minus 2A, the slope of this line. So the stress paths are assumed to be linear. If A dash actually varies with the test, once the test is in progress, then ideally the stress paths are curved in nature. So the effective stress paths will be curved in nature. That is what we have shown in the previous discussion. The reason why the effective stress paths are curved in nature, because the value of the A will not be constant. That is the stress, the effective stress, the Skempton's pore water pressure parameter A will not be constant. That is, the slope will be changing. So because of that, what will happen? If it is constant, then it is linear, and if A is constant, the slope will be constant, and then this is effective stress path. But if there is a if there is A varies with when the test is in progress, then ideally the stress paths are curved in nature. Now with the constant axial stress, once you look into it, so when we have got delta sigma, then which is actually nothing but is indicated by A, and which is nothing but when you have delta sigma and then no change in sigma dash, effective isotropic condition, and plus when actually C, that is delta sigma, is there, that then A is equal to B plus C, where delta sigma r dash is equal to minus delta sigma r is equal to minus delta sigma 3. So delta tau by delta sigma is equal to minus 1, and with this actually we can say that as B caused no change in the effective stress, and we can say that A is equal to C. So the effective stress path for undrained compression are same as both for constant axial stress loading as well as the constant radial stress loading. The effective stress path for the undrained compression are the same for both constant axial stress loading as well as constant radial stress loading. So here with this slide, what we are saying is that the effective stress paths for undrained compression are same for both constant axial stress as well as the constant radial stress loading. So when this is the constant axial stress, once you look into it, and so total stress path sigma r, then constant sigma A increase, then it is like this, and when you have the unique effective stress path is actually possible like this with the variation of the AF, and the total stress path total stress path sigma A constant and sigma R decrease, then it is actually traverses like this. So, influence of the stress paths on the laboratory measured undrained strengths, which actually can be given by this particular tau sigma sigma dash plot here, and this line is KF line, this line is the KF line, the failure line, and this intercept is K dash or A according to our notation, alpha dash or psi, and K dash cot alpha, that is this ordinate. So, we can actually get the delta tau by delta sigma dash as the slope of this line. So, slope of this effective stress path is 1 by 1 minus 2 AF. AF is the the slope of this line at AF is that pore water pressure Skempton's pore pressure parameter at failure AF. So, delta tau by delta sigma dash is equal to 1 by 1 minus 2 AF, that is the slope of this line. Now, if you look into this the at failure delta tau by delta sigma dash is equal to delta tau by delta sigma dash is equal to 1 by 1 minus 2 AF. So, at failure it is like this, referring to the previous figure, basically for the soil with initial stress tau naught and sigma naught dash. So, we can write tau F is equal to K dash. So, K dash is nothing but this ordinate plus sigma naught dash tan alpha, sigma naught dash tan alpha, that is the vertical axis ordinate, okay, and minus 1 minus 2 AF tau naught tan alpha dash. So, what we have written is that this particular vertical ordinate we have written, and that ordinate is actually working out to be K dash plus sigma naught dash tan alpha minus 1 minus 2 AF tau naught tan alpha, that is from the slope is actually known to you, and with that we can actually calculate. So, we are subtracting, we are taking the net height, that is tau F, and so with this we can actually simplify saying that tau F is equal to C dash cot phi dash plus in terms of C dash and phi dash parameters. So, we converting from the KF line to the tau sigma space completely, where with that tau F is equal to C dash cot phi dash plus sigma naught dash minus 1 minus 2 AF tau naught divided by cosecant phi dash minus 1 plus 2 AF. So, undrained compressive strength can be obtained where phi dash is equal to 0, undrained compressive strength is equal to can be obtained as tau F is equal to C dash cot phi dash plus sigma 1 dash divided by cosecant phi minus 1 plus 2 AF. So, here considering the undisturbed sample initially at negative effective stress, where sigma I is equal to minus UE and initially tau naught is equal to 0, So, with that this term will get when this will eliminated, then what we have is that the sigma naught dash is equal to sigma I dash. So, what you have got that C dash cot phi dash plus sigma dash I divided by cosecant phi dash minus 1 plus 2 AF, that actually remains here. So, based on the deliberation, let us look into the one problem here. Undisturbed soil specimens are basically taken from a depth of say at z is equal to 5 meters in a soft lightly over consolidated clay for which K naught is equal to 0.7. Undisturbed soil specimens are taken from a depth z is equal to 5 meter in a soft lightly over consolidated clay for which K naught is equal to 0.7, and the unit weight of the soil is 16 kilonewton per meter cube, and C dash is equal to 0, phi dash is equal to 22 degrees, and the water table is at depth ZW is equal to 1 meter, and assume that gamma W is equal to 10 kilonewton per meter cube. For specimens tested under a cell pressure of 40 kilopascal, assume that sigma V naught is equal to gamma Z, and if AF is equal to 0.8, find the undrained compression strength at CU, undrained compression strength CU. So, here AF, that is the effective stress parameter, Skempton stress parameter at failure is given as 0.8. So the solution actually works out like this. We can first get the vertical stress, which is nothing but 16 kilonewton per meter cube and 5 meter depth. So it is 80 kilopascals. The effective stress, because groundwater table is given at 5 meter, the groundwater table, water table is at a depth of 1 meter. So by taking these considerations, what we get is the effective stress. So once you know the effective stress, and K naught is given as 0.7, and sigma dash V naught is actually 40 kilopascals. So with that, what we get is that 28 kilopascals. So UE that can be obtained by sigma dash V naught plus 2 sigma H sigma dash H naught divided by 3, that is the sigma V and plus 2 sigma H. So that is this one we are actually estimating, and that is actually given as estimated as minus of 40 plus 2 into 28 by 3, which is minus 32 kilopascals, and tau f now is the C cot phi plus sigma dash right? That is nothing but which is obtained as obtained as this one as 32 kilopascals, that is UE is equal to that sigma A dash, that is 32 kilopascals. So cosecant phi, that is phi dash is given as 22 degrees, cosecant 22 minus 1 plus 2 into 0.8. So with this, the shear strength at failure works out to be 10 kilopascals. So similarly, another problem where undistributed samples are taken from a depth of 5 meters in a stiff heavily ore consoled clay, for which K naught is equal to 1.8, and because this is a ore consoled clay, the K naught will be high, and gamma 20 kilonewton per meter cube, and C dash is equal to 5 kilopascals and phi dash is equal to 20 degrees, and water table is at a depth of 3 meter, and assume that gamma W is equal to 10 kilonewton per meter cube, and for specimens tested under a cell pressure of 100 kilopascals, and if AF is equal to minus 0.15. So you can see that the AF is negative here, and find the undrained compressive strength Cu. So the solution again, sigma V naught is actually 5 meter, that is unit weight is 20, so 100 kilopascals, and the effective stress can be obtained as 70 kilopascals, and with 1.8 we will be able to get sigma H dash as 126 kilopascals. Similarly here now, by minus of UE is actually calculated, where the clay is more consolidated. So sigma V dash plus 2 sigma dash H naught H dash divided by 3. So with that, what we get is that minus 107.3 kilopascals. So tau f is equal to C dash cot phi plus sigma dash divided by cosecant phi dash minus 1 plus 2 AF. So by substituting this 5 into cot 22 plus 107, because here sigma dash is equal to minus this minus of minus will become plus here, and the cosecant 22 minus 1 plus 2 into minus 0.15. So with that, the shear strength of the soil works out to be around 87 kilopascals. So what we have done is that we actually have try to discuss about in the consolidated undrained triaxial test, and then we actually have obtained this deliberation about. So then we also have this octahedral plane, and where we have, for if you are having a sigma 1 axis and sigma 2 axis and sigma 3 axis, and then when you actually have these lines indicate that sigma 3 is equal to 0 and sigma 2 is equal to 0 along this line, and this is sigma 1 dash is equal to 0, and hydrostatic axis actually passes from the median of this, that is hydrostatic axis is equal to sigma 1 is equal to sigma 2 is equal to sigma 3 when it actually happens, and sigma 3 dash actually passes through this one, and sigma 1 dash actually passes through this vertex, and sigma 2 dash is actually passes through this vertex. But along this sigma 3 dash is equal to 0, along this sigma 1 dash is equal to 0, along this sigma 2 dash sigma 2 is equal to 0. So the octahedral plan is equal to octahedral plane is equal to sigma 1 plus sigma 2 plus sigma 3 is equal to constant. The octahedral plane is very near to the soil failure state, so very useful basically to derive the failure theories of the soil. So, this octahedral plane which is indicated as sigma 1 plus sigma 2 plus sigma 3 is equal to constant, and which is a plane which is very near to the soil failure, and so very useful to derive the failure theories of the soil. Further sigma octahedral, what we can actually get is nothing but sigma 1 plus sigma 2 plus sigma 3 by 3, and tau octahedral, the shear along the octahedral plane. That means that on this octahedral plane, that normal to the plane, that is sigma octahedral, and along this, that is the tau octahedral. So, we can get sigma octahedral as nothing but sigma 1 plus sigma 2 plus sigma 3 by 3, and tau octahedral is nothing but square root of sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square by 3. So, sigma dash octahedral is equal to sigma 1 plus sigma 2 plus sigma 3 by 3 minus u. So, and tau dash octahedral is equal to tau octahedral. So, total and effective octahedral shear stresses are equal. Total and effective octahedral shear stresses will be equal. So, from the Mohr Coulomb yield function, in most generalized form for the Mohr Coulomb condition of failure can be expressed as which is nothing but sigma 1 dash minus sigma 2 dash whole square minus 2c cos phi plus sigma 1 dash plus sigma 2 dash sin phi dash whole square plus sigma 2 dash minus sigma 3 dash whole square minus 2c cos phi plus sigma 2 dash plus sigma 3 dash sin phi whole square plus sigma 3 dash minus sigma 1 dash whole square minus 2c cos phi plus sigma 3 dash plus sigma 1 sin phi whole square. So, the Mohr Coulomb yield surface is indicated by this surface, which is indicated as GFEDCB, and A is the point of the intersection of the octahedral plane and the hydrostatic axis. This is the point through which through point A the hydrostatic axis passes, where sigma 1 is equal to sigma 2 is equal to sigma 3, and this is the point of intersection of the octahedral plane. So, you can see that these are the point of intersection of the octahedral plane. So, this is the octahedral plane, and the Mohr Coulomb failure surface is actually defined or limited by this GFEDCB surface. So, this is called as the Mohr Coulomb yield surface, Mohr Coulomb yield surface. So, then different failure criterions are actually described. So, what we do is that in the next class we will discuss more about the octahedral plane and the relevance to the how this can be interpreted for the so called understanding about the failure criterion, and then thereafter we will try to discuss about how we can actually determine E from the triaxial test data, and then we will try to do some example problems on the shear strength of the soils.